In this video, I will explain the realization of logic function using NAND gates. We have already studied NAND and NOR gates are called as universal gates. The reason is any logic function can be realized by only using NAND gates or similarly by only using NOR gates. So let us see how this is possible. We will take an example. A logic function is given as y is equal to a and b or b and c. So in the normal situation, if you want to implement this logic function, you require one AND gate for a and b, another AND gate for b and c, and finally one OR gate to join the two terms. So let us see how we can realize this logic function in a normal way, that is by using the basic logic gates. So here we have the realization of the logic function by using the basic logic gates. Here we have used an AND gate, here is another AND gate, and finally here we have an OR gate. Now the challenge is that instead of using these AND gates or OR gate, we should use only NAND gate to implement the same logic function. So we are going to see how this is possible. In order to understand the realization using NAND gate, one theorem will be helpful for us, that is called the De Morgan's theorem. De Morgan's theorem states that A and B whole bar, that is called as A NAND B, is equal to A bar or B bar, where this A bar and B bar is represented by a bubbled OR gate, where there is two bubbles representing the two NOT operation for the two inputs. Now the left side, which is a bubbled OR gate, is equal to a NAND representation, that is A NAND B. So we will require this De Morgan's theorem to replace any of those basic logic gates to a realization using only NAND gates. So let us start. We have the example y is equal to a and b or b and c, and realization using the basic logic gate is already available. And the first step is the same. You have to first draw the logic function by using the basic logic gates. And the second step is, wherever you have AND gates, you have to put a bubble and an inverter at the output of each AND gate. So here in this example we have two AND gates and we need to put a bubble and an inverter. The bubble actually represents a NOT operation, and the purpose of providing bubble and inverter at any output is that the actual logic function at the output doesn't change. If you put only a bubble, then the output will be the inverted value. But if you put a bubble and an inverter in series, the logic function doesn't change. So what is the next step? You have to put a bubble and an inverter at the output of each AND gate. So here we go. The output of the first AND gate, we provided a bubble and an inverter. Similarly, here we have another AND gate. So here also we have to provide a bubble and an inverter. So step 2 is completed. Hope all of you understood. Wherever you have AND gate, you need to modify it by providing a bubble and a NOT gate. We should not provide only a bubble or only a NOT gate because that will change the logic function. So Whenever you put a bubble, there should be a NOT gate to cancel that operation so that the logic value doesn't change. So that was step number 2. Going to step number 3. Put a bubble and inverter at each input of OR gate. So the next step is with reference to the OR gate. So here also you have to put a bubble and an inverter, but it is not at the output of an OR gate, it is the input of the OR gate. So here again remember we are putting a bubble and an inverter pair. So we have modified the OR gate with a bubble and an inverter, and it has 2 inputs, so both the inputs are altered in that way. Here again remember, as long as we provide a pair of NOT gate and a bubble, the logic function doesn't change. Let's go to the next step. The next step, we have to remove wherever we have NOT gates in pairs. So have a look at the implementation. We have the first part 2 NOT gates in pairs, and similarly on the second part there is another pair of NOT gate. So wherever we have NOT gates in pairs, we can remove them, and the redrawn diagram will look like this. So the 2 NOT gate pairs are removed. Now notice the first part, you already have NAND gates, and now the only one which need to be replaced is this bubbled OR gate. It is this time that we need to apply the De Morgan's theorem. You remember the De Morgan's theorem that a bubbled OR gate is nothing but a NAND gate. So what we need to do now? The bubbled OR gate at the output should be simply replaced by another NAND gate. So now that's it. Now look at the implementation. We had this logic function where originally we have AND operation and OR operation, but now look at the implementation. We are not using any of those basic logic gates, but we are using only NAND gates. So this is why NAND gates are called as universal gates. The same procedure is available for NOT gates as well.